In business analytics, we often want to compare multiple groups' averages to see which groups are different from one another, if all groups, for all intents and purposes, have the same overall average. And surprisingly, this is a topic that tends to get glossed over in pure probability or statistics classes. But since this is such an important part of business analytics, this is yet another one of these skills that is just extremely important to have once you graduate. And we talked about a related problem when we were comparing multiple groups in terms of the probability of some event occurring. So if we had three different, say, inventory control policies, how do the probability of stockouts compare across all of them? And we can use some of the data that you've already looked at and will look at to help motivate this. So with the returns data set that you analyzed for the homework, you had a column giving the return rate, which was the weekly fraction of products that got returned for various code names, different product groups that have been anonymized. And in the data, we have 19 different product groups. And so the natural question to ask is, well, are there any differences overall in the average return rates? And if so, what are the groups that differ from each other? It's a more complex question than just looking at two groups. We have 19 different groups that we want to compare. And for this upcoming homework, you'll be looking at characteristics of some of the most popular songs through the decades, from the 1950s through the 2010s. And so we might like to know, well, is there a difference in, say, the average energy that a song has, the average value of energy or danceability, or say the average beats per minute? Here we have multiple groups, and that's a more complicated question to ask than comparing two different groups to one another. And so this just happens all the time, especially in business analytics. We might want to be doing some sort of analytics in terms of, say, emergency responders and how fast that they can respond on average. And this could vary based on neighborhood in a city. It might vary from city to city. So where do we find these statistically significant differences? Who's doing great? Who's lagging behind? We'd like to know. Also, if you were trying to design, say, a hospital, trying to improve the quality of care for patients, you might like to know how the number of patient waiting rooms is related to the average waiting time, say, at an emergency room. So, is there a big difference in the average waiting time if there's 2 versus 3 versus 4 versus 5, maybe a whole bunch of different policies? We'd like to compare that average waiting time to see where the statistically significant differences lie. So, how do we go about doing this? How do we compare the averages of multiple groups? And I want to take us to the Cust loyalty data set once again, because it provides a pretty good motivator here. We'd like to answer the question, is there a difference in the average lifetime value of customers based on their income? So that lifetime value is the total amount of money that customer has spent over the course of their lifetime with that company. And here we have some broad information about what income group they belong to. So between or up to $30,000 a year, between 30 and 45,000, etc., etc. So if we run our aggregate command to get the average customer LV for each level of income, what we would find is that there looks to be a pretty steady trend here. As we move to groups with higher incomes, it looks like that average gets larger as well. Graphically, if we were to make a plot using just that same formula, customer LV, twiddle income here, data equals cust loyalty, we find that the median of the lifetime values seems to almost steadily increase as we move to customers with larger income levels. So, how can we statistically quantify whether or not we see any difference at all between groups? And if not all groups are the same, what groups actually do have statistically significant differences with each other? So, how do we go about doing this? And how is this different than just, sitting down and running t-tests for all of the groups that we would like to compare? So it turns out that if we do this kind of the way that it makes sense, the way that you might want to, where we just sit down and say, well, let's run t-test on the up to $30,000 group, and the 30 to 45, the 45 to 60, the 60 to 75, etc. We'll find that actually there are some pretty major shortcomings in just running t-test multiple times. What we'll actually find is that we really need to adjust the confidence interval procedure to make the range of values a little bit wider. So why is that the case? Why are there special considerations when we have multiple groups involved? Well, let's break it down. So we have 6 different groups of income. And if we were going to do all pairwise comparisons, well, how many different times would we have to run t-test? Well, it turns out that if we run the choose command, which we talked about very briefly when we were talking about the binomial distribution, if we wanted to choose, say, 2 groups at a time from a total of 6, that would yield a total of 15 pairwise comparisons. In general, let's say we had 100 different groups and we were going to do all pairwise comparisons. That would be choose 100, 2. But for our income example with 6 different groups, there's 15 possible comparisons. Now, here's the thing about our confidence interval procedure. By design, we've kind of set it up so that each individual confidence interval has a 5% chance of failing to cover the true parameter that we're trying to estimate, that's true value here. So 95% of the time, we know that a 95% confidence interval is going to do its job. It's going to cover the true value of the parameter it's trying to estimate. But 5% of the time, by design, it won't. So with 15 confidence intervals, well, 5% of 15 works out to be just about 1. By design, we're kind of setting up our set of comparisons for failure. We expect 1 out of those 15 confidence intervals to essentially get it wrong, to not actually cover the true difference. And that's not really a place where we would like to be, especially if we had more groups than that. If we had 100 total groups, well, the total number of pairwise comparisons we could set up would be just under 5,000. And if 5% of those are expected to fail to cover the true value of the parameter they're trying to estimate, that works out to about 248 confidence intervals that get it wrong. And we never know which ones get it right, which ones get it wrong, so we're kind of left up in limbo here as to, okay, which of these confidence intervals, are reliable, which ones are kind of missing the point here. And so this begs the question of, okay, how do we adjust our procedure to, make our set of confidence intervals a bit more reliable? So here's what we need to do. If the intervals are failing to cover the true value of the parameter they're trying to estimate too often, we can make those intervals just a little bit wider. Make it so they have more values, a better chance of actually containing the true value of that unknown parameter. And so what we'd like to do is make each of those confidence intervals wider so that as a family, as a collection, that collection only has a 5% chance of missing at least one of the true differences, say, between the different groups. So how do we go about doing that? And just to illustrate kind of the magnitude of this problem, I want to share with you 2 simulations. Now, in this first simulation, I want to compare 50 different groups to each other. So we're going to imagine that in each of 50 different states, we have information on 200 different customers. And by design in this simulation, I'm going to have it be that there's no difference in average value across these 50 states. Essentially, we're going to be picking random numbers for the customer's lifetime values from a normal distribution with a mean of 2,500, so every state has the same average, and a standard deviation of 500. So we're going to do all those pairwise comparisons, and with 50 different groups, if we choose 50, 2, that lets us know that there's a total of 1,225 comparisons. And we'll see how many of these confidence intervals for the differences in 2 groups, just coming up from t-test, actually end up kind of making us think there's a real difference when there's not, kind of discovering a statistically significant difference. So that's what this simulation does. It goes through and loops through all pairs of states and does that pairwise comparison with t-test. And it looks to see if 0 is inside that confidence interval. If 0 is not, then we're going to bump up the value of counter by 1 because we've discovered, quote unquote, a statistically significant difference. So after going through all of those 1,225 pairwise comparisons, we actually find that 41 of those confidence intervals don't include 0. Therefore fooling us into thinking that, oh, these 2 groups have statistically significant differences, and if we're using the results of these analytics to really make some pretty major decisions, we'd be fooled into the wrong course of action here. So that's really the key thing. We're not just doing this analytics for fun here. We're essentially trying to detect if there are differences between groups because we want to be basing decisions based on the discoveries. And every confidence interval that doesn't include 0 essentially gives us potentially some actionable insight. It indicates that those groups are differing in some meaningful way and that we might be able to treat or interact with those groups differently. So we really need to make sure that whatever procedure we're using to compare multiple groups to one another is doing this comparison fairly. So that essentially the true difference in averages between groups, they need to be falling inside our confidence intervals as a family, as a set, the desired 95% of the time. We don't want to be making tons of false discoveries and then making bad courses of action based on those. And for the second simulation, I think this really hits the point home. Let's imagine that we're going to do something similar to that last situation, but only 20 groups here, 200 individuals in each one of those 20 groups, all fundamentally with the same overall average. What if we didn't really know what groups we wanted to compare, say ahead of time? We wanted to see if there was any statistically significant difference between whatever group happened to have the highest average and the lowest average. Kind of makes sense that, if any two groups are going to have a difference, it's going to be the one that has the highest measured average and the lowest measured average here. So let's just see what happens in this simulation. By design, all groups have the same fundamental underlying average. When we go and take data, one of those groups just is going to have the highest, one of the groups is going to have the lowest. If we go through and essentially do this simulation 1,000 different times, generate values for each one of these 20 different groups, compare with t-tests just the difference in averages between whatever group happened to have the highest, whatever group happened to have the lowest, we find actually that over 90%, 93% in this simulation actually, of those confidence intervals detects a statistically significant difference in averages when we know, by design, that there really is no difference in these groups. So without this adjustment, we can really be fooled into thinking that there are statistically significant differences in groups when there really just isn't. Now, the great news is that this guy, John Tukey, a ways back, sat down and really thought hard about this problem and came up with a measure called the honest significant difference. So when we compare lots and lots and lots of groups to each other, we need to be making sure that as a family, those confidence intervals, comparing pairwise differences, are wide enough so that they, as a family, once again, only make a mistake 5% of the time. And so Tukey essentially is able to make that adjustment for us automatically. It's going to be able to really tell whether or not there are two groups that have statistically significant differences. So how do we implement this? Well, it's going to be the same procedure as what we did when we compared multiple probabilities across groups here. We're going to run the AOV command, short for analysis of variance, and we're going to set it up very similar. We want to be comparing the average customer lifetime value across all the different levels of income. So it's a three-step process in doing the complete analysis. Step one is defining that object called AOV that essentially just sets up all those comparisons. And then Tukey HSD goes and actually prints out the confidence intervals for all the pairwise comparisons that we might want to look at. So running these two lines of code and then printing out the results of Tukey to the screen, we go through and systematically get all pairwise comparisons. So if we wanted to compare the average lifetime value between those customers in the $30,000 a year and below versus the customers with the $75,000 to $90,000 income, we have everything we need. The data suggests that the difference in averages is right at about $840, and we're 95% confident that the true difference is somewhere between $435 and $1,237. Zero's nowhere to be found in that interval, so we found a statistically significant difference between these two groups, and one that's fairly large and one that seems to be pretty important actually if we wanted to base decisions on that. So Tukey figured out how to do this adjustment just right. If we really want to focus in on a particular set of groups, even if we don't really know what those groups are going to be ahead of time, the one with the eventual highest measured average and the one with the eventual lowest average, Tukey's got us covered here. So just to kind of illustrate that, if we go back and say, okay, Tukey, let's really put your procedure to the test, let's rerun that simulation where we went and compared 20 different groups with 200 members in each of them that all fundamentally had the same overall average. And after the data was generated, we glimpsed at the data and said, okay, well, this group has the highest average, this group has the lowest average. does Tukey's confidence intervals for those two groups, do the job the expected proportion of the time? So how often does it contain 0 here, that confidence interval? By design, we've set it up so that those groups really do have the same fundamental average. And how often does that confidence interval get it wrong? Well, if we go through that simulation and we count up the number of times where that confidence interval doesn't include 0, essentially we get tricked into thinking there's a real difference between those two groups, we find that it is getting it wrong the expected percentage of the time. We've designed our procedure to have it cover 0 95% of the time, the true difference. It's going to miss it, it's going to fail to cover that 5% of the time. It's going to lead us into thinking there's statistically significant differences when there's not. And it looks like with this adjustment, we're all taken care of. So going back to the lifetime value example here, let's go ahead and just fit that. So we are going to be looking at the customer lifetime value based on income here. Getting the table of averages, well, I should probably load up that Cust Loyalty data set. We have that trend where customers with higher incomes tend to have higher averages for their lifetime value. We'd like to know, all right, what about the 30 to 45 versus the 90 and above range? What about the one with the overall lowest, the 30 or less, and the overall highest, the 90 and above? Let's do that analysis. So we set up the AOV, essentially the same syntax as when we ran aggregate, just a little bit simpler. We don't have to pass a fun argument. And then we say, Tukey, come to the rescue, and we'll look at the honest significant differences between these groups, and we'll print out all pairwise comparisons. So if we wanted to know, all right, is there any statistically significant difference between the 45 to 60K group and the 75 to 90K group? Well, here's our confidence interval. It includes 0. No statistically significant difference in average lifetime value for those two groups. Looking back at the group that had the lowest, 0 to 30, and the highest, 90 to infinity, we just got to hunt through here. We found it here. Is there a statistically significant difference between these two groups? Well, yes, there is. The 95% confidence interval is 740 to 1620 or so. 0 is nowhere to be found in that interval. So yes, we would say that there is a statistically significant difference. Now, one drawback from comparing all these different groups is that it's very difficult to scan through this list and really make sense of it all. And so very similar to when we compared probabilities across multiple groups, we are going to make a connecting letters report to make our lives a little bit easier. So how do we read the connecting letters report? Once again, let's review. So after we've made Tukey, we can load up the molt comp view library and ask for molt comp letters 4. We'll pass our AOV object and our Tukey object, and we'll get this connecting letters report. So how is this set up? Well, it is set up so that groups with letters that come earlier on in the alphabet have higher averages than groups with letters that come later on in the alphabet. And that's what we had seen before. If we refer back to our table of averages, 90 to infinity had the highest, 0 to 30 had the lowest, 90 to infinity had an A, 0 to 30 had the D here. So they're ranked in terms of highest to lowest average here. Now, what does it mean when we see an A under multiple groups? That means that if we were to go back and look at the confidence interval, that confidence interval would include 0. So we see that both 90 to infinity and 75 to 90 both share the letter A. Well, can we find them in this list? Well, it happens to be at the bottom here. Notice this 95% confidence interval contains 0. So whenever we see two groups that share the same letter, we say that there's no statistically significant difference in averages between those two groups. Whenever they're connected by the same letter, no statistically significant difference. Now, if we find two groups that don't share a same letter, like 90 to infinity and 45 to 60, 45 to 60 has a B and a C, 90 to infinity just has an A, the implication is that 0 is not going to be in the 95% confidence interval. So let's hunt for that one, the 45 to 60 versus the 90 to infinity, right here. And just as expected, that 95% confidence interval does not include 0. So we say that these two groups have statistically significant differences in the average, and that's how we use that connecting letters report. It provides us a nice little ranking of highest average down to lowest average, and we can very quickly go and look to see, well, where are the statistically significant differences in groups, and which groups basically look to have the same average. Sometimes the data can discern a difference, sometimes it can't, and that connecting letters report really helps us out. So another example of this, I think interpreting connecting letters reports is kind of fun. Let me load up the Bulldozer 2 dataset here. And in the Bulldozer 2 dataset, we are looking at prices of bulldozers that are sold at auction, and we might want to compare the average selling price on a decade-to-decade basis. So if we plot the selling price versus the decade, data equals bulldozer, we see that, okay, it kind of looks like bulldozers that were made more recently tend to sell for a bit more. But we don't expect, expect perfect correspondence between each of the groups when we collect data. Let's go and try to spot the statistically significant differences. So let's get out the table of averages just by running aggregate here, making sure to add the mean function for what we're calculating for each group. So more recent the decade, higher the price. Where are the statistically significant differences? So let's run that AOV command. Same formula here, very little adjustment. Then we'll invoke Tukey to help us out with fair comparisons. We can print out the contents of Tukey to get all pairs. And then we can ask for that multcomp letters for the connecting letters report. And so what do we see? Well, bulldozers that were made in the 2000s have the highest average, and the farther back in time we go, that average tends to decrease. So where are the statistically significant differences? Well, it looks like the average from the 2000s is different from all the other decades. There are no other groups that have A being shared with it. The average for the 90s is different from all the other decades as well. It's the only one with a B. And it looks like there's no statistically significant difference in the average sale price for bulldozers sold in the 1980s versus the 60s and 70s. And in fact, going back to the 1980s, 60s through 70s comparison, we see that 95% confidence interval, including 0 right here. So unlike when we were having this discussion for comparing probabilities across multiple groups, there's actually some additional assumptions that we need to check about the data for this analysis to be reliable. So all of those confidence intervals for those pairwise differences that emerge after we've invoked Tukey to help us out, we, number one, require that all the groups are independent of one another. So we have no sort of pairing or dependency or relationship between the values in one group versus another group. We have that paired t-test for like before and after weights or sales, before an advertisement, after an advertisement. This sort of analysis only is going to work if we're dealing with all samples being independent of one another. And number two, we need to make sure the sample sizes for each group is large enough. That's tied into the shape of the histogram. If it's roughly symmetric, about a dozen or more data points is fine. If there's a little bit of skew, at least 2 dozen for each group, and we're good to go. If we have at least 100 for each group, we can invoke that central limit theorem, we're good to go. And then finally, there's an additional assumption, one that we haven't actually talked about for any other test or line of analytics that we've done. And that is checking to see if the standard deviations of the data values for each group are identical. It turns out that Tukey and this analysis of variance technique requires this to be the case, or at least close enough to identical, in order for the numbers that get spit out by the procedure to be considered reliable. And I typically just like looking at this visually. If I look at a distribution of the values inside each one of the different groups, I want to see the box plots look about the same, at least in terms of the spread of values, the width of the box, the size of the whiskers. This would be 3 groups that have just about the same standard deviation, the same spread in their values. This would be an example where that assumption would very clearly be violated here. Group A has, quite a large standard deviation. B, super, super tiny. The values are very clustered around the average. C has about the same size standard deviation as A, with some outliers here too. So that's an additional thing we have to check, and let's kind of cross our fingers here. All right, one last thing that I want to bring up before we close out this unit on comparing averages, or even just getting a confidence interval for just a single average, is whether or not we should be actually focusing in on the average itself. Now, in business analytics, a lot of the time when we look at a histogram of the data values, we see something like what we see here. These are the histogram of donation amounts to a veterans charity, and it's just super skewed. So almost all the data values are concentrated in this very lowest bar, and we have some representation for lower or for higher values, but they come at a lower and lower frequency. Almost everything else in business analytics kind of looks like this. Now, when that's the case, the average may not be measuring what we'd like it to be measuring. We'd like the average to summarize the typical value we could see from that distribution. And when we're dealing with a very skewed distribution like this, the average may not really cut it. So, similar example just to illustrate this point. Here's a nice skewed distribution. The data is actually coming from a log normal distribution. And here this red line is representing where that average is. Well, technically, yes, that's how you calculate the average. You sum up all your data values, you divide by how many there are, and that happens to be where the average is for this data set. And think to yourself, does this really do a great job of indicating what a typical value you might see? Well, I don't know about you, but I would probably prefer something maybe closer to the peak around here. That's kind of what I consider a bit more typical. And so here's one of the tricks that I like doing when I do have a very skewed distribution like this. I actually work with the logarithms of the values themselves that were originally recorded. So same data set, but instead of looking at the raw data values, here's the histogram of the logs of those original values. Notice how nice and symmetric that is. I'm much more comfortable doing analytics in this realm. And in fact, most of the techniques in the analytics toolbox are designed to excel when they're dealing with symmetric distributions. So if we were to do the analysis on the logs, like get the average of the logs, and then untransform that, kind of convert that back to the original scale by taking 10 and raising it to that power, well, here's what happens. So here's the distribution of the original data values. That red line is the sample average, kind of far away from the peak, not very representative of what I think a typical value is. But if instead we went and got the average of the logarithms of those values, and then untransformed that value by taking 10, raising it to that average of the logs, we get the blue line here. That's kind of converting the average of the logs back to the original scale, and that gets a little bit closer to the peak, and I feel like that does a bit of a better job at summarizing this typical value. So in business analytics, very often we're going to find ourselves just living in a logarithmic world. Those originally recorded data values might yield such a skewed distribution that we're better off actually analyzing the logarithms and then just transforming it back to the original scale so that it's easier to interpret those results.